right, so in the previous lectures, we made up counters, synchronous up counter, synchronous down counter. We can create a counter that does both. It count not at the same time, obviously, but it will count either up or either down. So these are called bi-directional counters, also known as up-down counters, capable of counting in either direction through any given count sequence. They can be reversed at any point within their count sequence by using an additional control input. That control input will obviously control whether they count up or count down. Right? And so we'll define this in our circuit as the circuit will work as an up counter when the control input is 0 and will count down when the control input is 1. So control input 0, we count up. Control input 1, we count down. Right, and so here I've got a truth table for the up-down counter. Right, we still have our present state inputs. It's a 3-bit up-down counter. We've been working with a 3-bit counter. So our present state, right, we have 8 possible different states, binary 0, 0, 0 to 1, 1, 1. Here's our additional input now to the state machine, right? This control direction where we said 0 counts up, 1 counts down. So I called the control M. In this particular case, when M is 0 in this half of the truth table, we have these 8 different states. We said we want to count up. So in this part, if our present state is 0, right, if our count's 0 and we're counting up, our next state should be 1, 0, 0, 1. If our present state is a count of 1, we're counting up by 1. From 1, we go to 2, 0, 1, 0. From 2, we go to 3, 3, we go to 4. You get the idea, 4 to 5. Remember when we're at 7 in the up counter, 1, 1, 1, our next count is 0. We cycle back around. And now in the other half of the truth table, right, we replicate these present states, but now our control input can be a 1, and we said we down count. So remember with a down counter, when our count was 0, we counted down to 7. Right? When our count was 1, we count down to 0. 2, we count down to 1. 3, we count down to 2. So here is where the next state comes from. Right? You can now derive these equations. So once again, if we use D flip-flops, we know that the input of D2 will be equal to Q2 next, the input of D1, Q1 next, the input of D0 will be equal to Q0 next. So you can then put these on a K-map, right? The Q2 next, it gets its own K-map, Q1 next gets its own Q0. And then that K-map is dependent on, so D2, which is Q2 plus, is a function of M, Q2, Q1, and Q0 of these 4 inputs. Right. And so then once you derive the equations, I've just shown the equations here, right, that D2 is a function of M, Q2, Q1, Q0. Well, I'm showing the 1s, 3, 4, 5. So you can see the 1s are at, so this is your entire input. So here's 3, here's 4, here's 5, here's 6, here's 8, right? There's 13, 14, and 15. That's where these come from. Because remember, all 4 of these now are your inputs, M, Q2, Q1, Q0, present state. And so we derive then an equation, right? In this particular case, if you work through this, you'll see that the equation comes out to be Q2 XOR with Q1 and with Q0 not. Remember, our equation for D2 for the up counter was this. Our equation for D2 of the down counter was this. This additional control is simply choosing whether we up count or down count, and this looks like a mux. What I'm calling M here, if we call this S for select, right? The M is your select bit, right? When the select bit's a 0, right, this will flow through. When the select bit's a 1, this will flow through. In other words, right, when select is a 0, or when the control is a 0, we get the up count. When the control is a 1, we get the down count. So this is mux behavior. So your other circuits then will look like this, is very similar to this as well, right? In this case, remember then our we had Q1 XOR with Q0 for our other counter, right? when you go through the Boolean algebra, you can also then say this is an XOR relationship. So here, this was the relationship of our up counter. This was our down counter for D1. We've simply ended on this control, the selector. So that's why I say note the mux behavior here. And then if you didn't want to implement this with a mux, right, you could go ahead and use an XOR gate here. You can't XOR, you can't XOR this one, but you can this one. All right. And then D0, well, D0 still ends up being Q0 not. That doesn't change, right? And your schematic looks like this. Now it depends on, in this case, I'm not using a mux. So for this particular circuit, we've got both the up and the down counter in here. All right, we've still got our 3D flip-flops. We said that the D0 is Q0 not, no matter whether we're up counting or down counting. That simply came from solving the truth table. I won't start to scroll back up to that. Don't need to do that. Right, here's our flip-flop D1. Well, we said D1 is if we go ahead and implement then, right, this circuit behavior was here. D1 was, M naught ANDed with Q1 XOR with Q0, M ANDed with Q1 XNOR with 0. So I didn't simplify it down to this in the circuit equation. I left it in this particular form here. Right? And so you can see M is ANDed with Q1 XNORed with Q0. Here's M naught ANDed with Q1 XORed with Q0. Could have simplified it by putting in another XOR gate. What I wanted to do, the reason I didn't is I wanted to leave it in the form where, notice I've got this box that I drew around here, where this is mux behavior. Right? What I'm trying to point out is here where we're saying this is mux behavior, means we can get rid of these gates and we can put in a multiplexer instead. Right, here's our D2, right, with the XOR gates, right, the AND gates. Here's our equation for D2 that we implemented. If you go back up and look at that, you can see this matches that long form of the equation. But once again, I want to point out the mux behavior here, right? So you can build this circuit, right, simulate it, see that it works, but you can also replace it with a mux as well. Right. I've got that here in Quartus, right, where we've got the mux behavior. But I've also got then this particular behavior as well. Let me turn on the annotate again. Right. And so we've got the clock. I called it direction instead of M. It was M in our truth table. Here I called it direction. And notice then that circuitry where we showed the mux behavior here, I simply replaced that here with a mux. So this is a Quartus library. So LPM is library parameterized module that let me create a 2-to-1 mux, right? I've got data input line 0, data input line 1. Here, then I'm showing M as the control. Well, we do have M in the circuit. What I call direction on the input, I labeled that wire M. So here's your M here. That matches your circuit equations. Like I said, I want to show you that we could simplify that circuitry, that drawing a bit by putting in the mux. I want you to be aware of that mux behavior. We look for that whenever we can to simplify a circuit. And this is a fairly complex circuit, right? It simulates, right? When you run the simulator, it will work correctly. Right. And that's, so here's an output of the functional simulation here from that circuit, right, of the up-down counter. You can see it starts out, so here, what I call direction on that input pin. So when direction's 0, we say we should be up counting. So 0, 1, 2, 3, 4, 5, 6, 7. I let it roll over to show that it rolls back over. We also said at any time, we should be able to switch the direction and switch our count. So here direction goes from 0 to 1. Now remember, flip-flops are triggered on the rising clock edge. So it's about 100 nanoseconds you have that rising clock edge where your direction signal will be 1. Your count will reverse to 0, 7, 6, 5, 4, and will go down again. Right. If you run the simulation out, right, and you change direction again, you will see it start up counting on the next positive clock edge. Right. Like I said, here's where I show you where I actually then use this LPM mux and this mega plugin wizard to create a mux. So I didn't have to create a separate mux circuit, right? I can use these LPM muxes that are already defined within Quartus, and I can tell it then, right, how many input lines. I want 2 input lines. How wide should each one? Well, I just want each one to be 1 bit. Right. Clicking on next, clicking on finish. So this walks you through then how to create that. Here's what this particular symbol looked like then when it was created, and I could add that into the project. And this then, of course, shows the circuit that I just showed you in Quartus, where I replaced that mux behavior with a mux circuit. And if you run the functional simulation with that, on that circuit, you will get the same behavior. We will see that you count up when your direction is a 0, you count down when it's a 1. And so now we've got this circuit that can either count up or count down depending on the control signal. Right, so that's called a bi-directional counter. All right. So that is it for how to do this with the flip-flops. Right, you'll be doing something similar in homework. All right, thanks for watching. Ask your questions.